Can you hear me? Is it? Okay, perfect then. So hello everyone, my name is Timothy. I am a PhD student in Astron, the Netherlands Institute for Radio Astronomy in University of Groningen. My supervisor is Harish, which is over here, as you can see, and Joe, also in the audience over here as well. So just like SK and ngVLA being the new eyes on the universe, Harish and Joe is the new eyes on me. So yes, today I'll be talking about radio emission as a stellar activity indicator. So I already know what you're gonna say. Where's the word disk in this title? I don't see the word disk exactly. So I have to try to convince you guys why we even care about stars in the radio. Because when you talk about stars, we talk about optical, infrared, X-rays. So radio must bring something new to the table, and indeed it does. Otherwise, I should be leaving right now. So in fact, it's interesting because plasma oscillation and charges moving in magnetic fields all emit in radio waves. So this gives us basically an excellent probe for this kind of dynamics. And this, for example, allows us to study, for example, the corona of the stars or even magnetospheres of exoplanets. And it gives us like a lot of insights, for example, on exo-habitability, for example, like how stellar plasma would impact exoplanets, how to have some direct measurements of the magnetic field strength of exoplanets, or how the corona is heated, for example. And so the natural question one comes to mind, or at least I come up, is, well, we come up obviously, is what exactly is powering the radio emission of these kind of objects? What is the engine that provides the energetics for this kind of dynamics? So there are two objects. So one is called a sunlight object. So basically we have obviously the sun, and mainly is powered by all these kind of flares, big boom booms that basically provide a lot of energies, and sometimes even so energetic that it can pump up plasmas, corona mass ejections, all this kind of fun stuff. And this is the things that provide the energy. But on the other hand, we have Jupiter. And last time I checked, Jupiter does not flare. So what's going on? Because Jupiter is actually brighter than the sun in 40 megahertz most of the time. So at the end of the day, it's because Jupiter has a very strong magnetic field, but more importantly, it's also spinning very fast. So usually back in the Netherlands, I can just say the word bicycle and people will be like, oh, I understand that. But let me try to elaborate because of a dynamo effect. Oh, shoot. Dynamo effect is basically charges moving in a rotating magnetic field, accelerates, radiates in radio waves. It rhymes. So at the end, basically what we really want to try to find out is basically sort of a transition between the two, because on the one hand, we have these just our FGK stars on the sun-like objects. On the other hand, we have basically scaled up versions of Jupiter, like brown dwarfs or even very late Ms. And obviously you want to find basically a bridge between the two, and the bridge is going to happen in M dwarfs. But it's also just interesting to study M dwarfs in general in radio because most rocky planets revolves around M dwarfs. So it's just interesting to understand what the plasma environment of this kind of system is. So now we understand the motivation. We now need a sample, and what better to actually look at a radio survey. And I won't be preaching to the choir here. We all know what LOT and VLASS is. And we all know how awesome it is in terms of sensitivity. Basically, this is a graph that you want your instrument to be as low as possible so that you can say, oh, my instrument is the best, give me more money. So it's basically high resolution, high sensitivity, awesome. But obviously, this is where the connection to SK and ngVLA is going to be, because if it does exist, obviously, eventually it will be somewhere in the bottom. So yay. So that's it. But also we want to find stars from this kind of radio survey. So obviously we need a star catalog. I wonder what that could be. Gaia, of course, Gaia. But also I won't be boring you with details, but most importantly, Gaia, we use Gaia catalog of nearby stars, just showing the solar neighborhood. But most importantly, we use this because it is actually complete, very complete up to 50 parsecs, up to very late M. So we now have a volume complete sample. And because we want to find a transition, right, we need this volume sample to actually find trends within spectral type, moving from basically solar type stars to M dwarfs. And so here are the results. This is just an HR diagram. On the left, we have the LOFAR sample, radio sample. On the right, we have the VLA sample. And obviously, you can see a bunch of interesting dots here, but all we really care about is basically population, right? So let me just bring you through what exactly makes up the bulk of this detection. So on the upper left, you can see there's these blue and purple squares. These are the chromospheric active binary stars. or at least most of them are very close binaries. So basically RCVNs, BOI-dwarfs, these are stars that have like orbits of days or even hours, so spin much quicker than their main sequence counterparts. And on the other hand, so in these kind of stars, basically they interact with each other a lot as well, and they're very closely active. So these are like basically radial powerhouse. And on the other hand, we have our favorite M dwarfs. There's a bunch of them, a lot of red and orange dots here. Just also, and this mainly makes up the bulk of the detections, as you can see in this survey and in the radial sample. But one interesting thing that I'll gloss very quickly is basically you see a lot of, especially in the VLASS sample, you see a lot of M dwarfs actually deviating from the HR diagram, which tells us these are very likely to just be close binaries as well. So now, but obviously, looking from this picture, you might just say, oh, well, I see a lot of M dwarfs here. So it means that this is where the transition happens, because if there's Sun-like engines and Jupiter-like engines, we expect they have very different efficiency, they have very different detection rate as well. So we might say, oh, I see a lot of M dwarfs, so it means that the transition happened here already. But we need to, at the end, compare to the background population, because just much more stars, much more M dwarfs compared to any other stars, right? So we actually need to do something, a comparison between the radial sample and the background population. And what we did is basically do something called just a CDF, a cumulative distribution function. So let me bring you briefly, very quickly. The x-axis is gone. The x-axis is Gaia colors, just BP minus RP. I don't know why the x-axis is gone, but just trust me on this. And it's from 0 to 1. What does that actually mean? Let me actually bring you a more intuitive way of understanding this. So let's draw a line at M0, for example. Hey, there is the line. And as you can see, the blue line is the Gaia background distribution. So just the population, Gaia population itself. The orange line is the LOFAR sample. The gray line is the VLA sample. As you can see here, for the gray line, it's around 0.4. So 40% of them are basically earlier than M0, and 60% of them are later M0. As you can see, for the Gaia, it's actually more like a 20-80. And at the end, the error bars, so basically the shaded error is just the 90% confidence level in terms of binomial errors. And so now we can actually compare how different it is compared to the background population to see if there's a transition. And as you can see, there's already a huge, oh no. Okay, there it is. Okay, so as you can see, there's already a very conspicuous bump here. So these are the aforementioned RCVNs, BOI-dwarfs, et cetera. So, and compared to M dwarfs, for example, right, we have like tens of thousands of M dwarfs just in our solar neighborhood, and it's only like 100, maybe 200 of RCVNs, all these kind of things in our solar neighborhood. So it already means that they're much more likely to actually find these objects compared to any other main sequence star. So let us actually remove this, because we know they're very closely active, they interact a lot, they emit radio very strongly. So let's actually remove them from this population, because we were trying to find basically run-of-the-mill main sequence stars. So now, as you can see, we remove the bump, and all there's left is the rest of the population. And now we can basically do something called a KS test, just comparing two populations and see whether they could join from the same population, from distribution. In this case, we're comparing Gaia to the radial sample. And the ideal case is that we want to have a low p-value. Basically, lower p-value means that they're not drawing from the same population. So it means that there might be a transition. So for the LOFAR one, it's 10%. It's like 10%. So it's not enough. So we need more detections, SKA. But on the other hand, we have the VLASS one. It's much smaller error bars, and as you can see, the p-value actually reached much lower than 5%. So we can confidently say that it's not consistent with background rate. So this means there is an evolution in radio detection with spectral type. But just a side note, the dip happens around M4, which is interesting by itself. This is just a zoom-in version of the graph, because that's where basically M dwarfs turns into basically fully convective. Maybe it's interesting, but I digress. So. And then we know that now there's an evolution in radio detection, but does it actually depend on other known stellar activity indicators? So one thing we look at is flares. So I hope everyone agrees that the more a star flares, the more active it is. No objections, perfect. So we look at X-ray flares, for example. There's a study by Johnson. Oh no, spoilers. Okay, so basically just says, again, this is just spectral type, basically from late M's to up to G dwarfs, a little bit higher, and this is just flare rate. So you can see G actually flare more, like 10 times more than a typical late M star in X-ray. So so we just have to multiply this to the Gaia background population, and if the radio population does indeed follow the X-ray statistic, after the multiplication, it should match. Well, it doesn't. So again, this is just the exact same plot. Again, this time in stellar mass instead of Gaia colors, but it's get the deal. It's just a proxy of spectral type. And as you can see, now this is the original Gaia distribution, and now you multiply this, basically it boosts all the G stars, and then less and less and less until you get back to 1 again. And as you can see, just by eye, it's not consistent at all. So we can confidently say that radio does not correlate with X-ray flares. But on the other hand, we also have optical flares, which is what TESS can give us. So the transiting exoplanet survey satellite basically look a bunch of stars for a very, very long time in hopes to look a lot of, to search for exoplanets. But obviously, because it's looking at a lot of stars, so they stare at a lot of stars, amazing flaring statistics. And here, a study by Gunther actually conclude is the other way around compared to X-ray. M dwarfs somehow actually flare much more than any other star. So M, you see late M's actually 50% of them are actually flaring, and anything earlier than M basically 0. But there's a lot of biases in this study. So at the end, I won't bore you with the details. If you want to know more, you can ask me, obviously. A bunch of biases, we de-bias them. It's a cool boxing gloves. And basically, after all the biasing and then multiply it back to the Gaia background population, we have this as well. Now, it looks more or less similar, quite similar to the X-ray as well. As you can see, it boosts the G dwarfs up a little bit, and then a little bit dip, and then boosts it back up a little bit again. But again, as you just tell by eye, also by the p-value from the KS test, that is also not consistent with radio as well. So radio does not correlate with optical flares either. And so just to briefly at the end, because I'm legally obligated to mention this, right? So what does SKA and ngVLA does for my work, for example, for our work? So obviously sensitivity, great, 10 times better most of the time. And obviously in an all-sky survey, the number of sources that you have is proportional to the flux threshold. So it means that the original graph that I have that I cannot conclude for the LOFAR sample now will become this. Wow, you can't even see the error bars anymore. Actually, you can, but still. As you can see now, it's basically smallify the error bars. So now instead of a p-value of 10%, you have now 0.0000000. You get the point. So it basically gives us a more, just a more confident way of saying there is a transition or not. But that's it. Before I move on to the conclusions, yes, I just have a quick public announcement. So there's a Science at Low Frequencies conference, December, Amsterdam. How low can you go? Just at the end, first come, first serve. So Joe is organizing this, so I'm legally obligated to say this, otherwise he'll knee strike my FIDOs. So be here. If you're not just about planetary radio emission or stellar radio emission, also like EOR, FRB, all this kind of interesting stuff. So be here or be somewhere else. So in conclusion, the bulk of the radio detection are the very close binaries on one hand, so the RSCV and BOI DRAS, these basically FGK close binaries. On the other hand, we have M dwarfs. And there's a radio activity actually evolves with spectral type. As we can see it confidently in the VLASS population, and especially the transition happened in M4, which might be interesting by itself, but it does not correlate with any other, with optical and X-ray flares activities. So there must be some sort of connection between these two populations. So we think that it might be just that radio is actually tracing all this kind of large-scale stellar magnetic field strength. And of course, SKA and ngVLA will increase the sample and make it more confident in our analysis. So that's it. Sorry to this crowd. I just realized I never looked at this crowd.
Great, thank you for a very energetic talk. So Tom.
Okay, so that was really interesting. I have a quick suggestion and then a question. So the quick suggestion is if you have a 10% p-value with a KS test, you might push that over the top by going to an Anderson-Darling test, which is usually a little bit more sensitive.
Okay, perfect.
And then the question was, when you had the Hertzsprung-Russell diagram with the radio sources on it.
Give me 1 second.
Yeah.
All right, it doesn't work. Okay, you can continue on the question.
Yeah, you had a few objects that looked like they were above the binary sequence. Do you know what those are? Are they like sub-subgiants or something like that?
Yes, in fact, they are. Most of some of the RC events are basically subgiants or even giants at some point as well.
No, I'm talking about things that were like above the late dwarfs.
Oh, the late dwarfs. No, for
right.
more
So
we
you
can...
kind of showed the binary sequence, but that's 0.7 magnitudes at most, and you had something that was like 2 magnitudes. You see?
Yeah, and that's what I thought as well. And I think it's just because I think it's close by because maybe it's just because they merge together in Gaia, so that you can't even screw up the Gaia, the colors as well, or.
No, I mean, if you have a equal mass binary, you go like 0.7 magnitudes above the main sequence. But if you look at the brightest things, they're much more than that.
Yeah. So I think this definitely warrants more investigation on what they are. It might be also like some giants, but then how do you mask them exactly with an?
There's a class object called sub-subgiants that I think those might be. Maybe we can talk later.
Okay, yeah, of course.
Yeah, great talk. Lots of fun stuff. I was wondering if you played any games with your non-detections, either in terms of stacking or with trying to extend the KS tests and the like to include non-detections.
How exactly would that be done? Exactly.
You can look at a paper by Joanna Lees from sort of late 80s, I think. We went into the upper confidence limits and how you employ those and error bars and that sort of thing. It might be interesting. Stacking is the really easy way, of course, because you have tons of non-detections. You should just be able to add up all your stuff in color bins or whatever you feel like with appropriate weighting and see whether you can pull any radio up.
Well, the main problem is that because in radio, radio are very variable. It's like these kind of radio bright stars, those are very variable at the end of the day. So maybe it's just because the non-detection doesn't mean it's not radio bright by default. It might just be radio we got along key as well.
Yeah, that was my other question.
Okay.
That's how you accounted for variability, and are these like, well, you think you're only detecting the few in the population that you happen to hit when they were flaring, is that okay?
Yeah, at the end.
But then you should be correcting, well, I'd be interested to know whether that means that all of these are the same. Is it consistent with all of them flaring, and you just, what does that give you for a duty cycle?
Well, we did check, for example, for the sample we have, we checked, for example, because they also observe in tests as well, some of them, in fact. So we actually look at the flare rates of these stars individually and see if there's a particular trend. Like, for example, maybe they're all flaring very, very rapidly as well. But we can't see them either. We also look at other activity indicators like H-alpha. For example, Joe back then already looked at the M dwarf sample here with see if they correlate with some other known activity indicators like rotation period, Rossby numbers, H-alpha, but we can't exactly see a very obvious trend.
Hi, thanks for the very nice talk. My question, so you've made a case, right? Hi, I'm here. You've made a case for going deeper in the radio, but I was just wondering, have you considered, or are there any gains to be made by going deeper in the multi-wavelength studies that you've done to further, improve the confidence on your results?
Maybe because, but that's the original motivation of looking at these two populations, because they're probing in different frequencies, right? So this is meter wavelength, and this is back to the classic gigahertz for stars. And originally thought basically the gigahertz will be more just akin to gyrosynchrotron. So basically like what we see on on flares of sun and other stars. And these, because they have a much lower frequency, so it's much more likely for them to be actually from coherent emissions just by default, because of the inverse content limit. So we thought it's just probing different populations. And just because it shows up here doesn't mean it's showing up here. So I'm not entirely sure whether a multi-wavelength, just having them both in the same time would increase our confidence on the transition, but who knows?
Okay, so let's thank Timothy again.